Alright, hello. So this is a kind of recap video of the office hours we had for AP Physics 2 on Thursday, May 7th, kind of as a review for the AP exam. I really want to say that the big message right now is that looking at the big picture, not worrying about the details, staying mentally fresh, that's really the most important thing. So we spent a long time going through details, and I hope that made people feel better. But I mostly think right now you should be studying things like your concept maps. If I do this kind of problem, what's the big picture? If I do that kind of problem, what's the big picture? So please don't get bogged down in details right now. You're all good students. You're going to do well on this. I think one thing to keep in mind is that for almost every topic, there are two overarching themes. Sigma F equals MA and EO equals EF. Dealing with force and how things move and change their movement, and then dealing with objects that switch from one location to another have really been at the heart of this course. It's not true for every unit, but in the back of your head, those two are things you probably should be thinking about. Just a quick little tour of what we did in the meeting, just so if you want to kind of review this or if you weren't there, you know. So we started in the fluids unit because students had questions about that. And I wanted to point out that even things that don't look like they come from the force equation ultimately do. So you can derive a lot of the understandings of this course from sigma F equals MA. Student asked if you can use this when water's in motion from one place to the other, and the answer is no. You need to use two other equations. The continuity equation, and this one I feel like should make sense to anyone who's ever put their finger over a hose and sprayed somebody. And then the Bernoulli equation, which ultimately stems from EO equals EF. So as you work down, essentially you can see that kinetic and potential energy get joined by work being done, pushing water one direction, pushing water the other direction, and that ends up being pressure. So anytime you're dealing with changes in height and motion and pressure, you really want to be using this. It's not always this complicated. You won't always use every term in Bernoulli's equation. And in our Torricelli's law experiment where we had water flowing out of the side of the bottle, we basically had a lot of these terms go to zero depending on location. Terms in different locations go to zero. So you want to pay attention to what's the pressure in this location versus that location. Has it changed? What's the height in this location versus that location? Has it changed? And same with speed. So anytime you've got potential of things moving, you do want to start with the Bernoulli equation. The last thing I said for this part was that, you know, even if you got a question that doesn't look like it has anything to do with anything you know, sigma F equals MA and EO equals EF are the ways to be thinking. So this question ended up being a sigma F equals MA question. And it ends up getting unfamiliar quickly, but have confidence. This is something you've practiced a long time. And if you're ever kind of stumbling over what to do, sigma F equals MA or EO equals EF are a good place to start. We spent a fair amount of time talking about thermodynamics. And kind of the big things to repeat are just understanding that the overall work in a cycle, a thermodynamic cycle, is the area bounded by the cycle. So work is done in process 2 equal to this pink graph. Work is done in process 3 equal to this green graph. So the overall area is the stuff that's inside that shape. We also went through what the different thermodynamic processes represent. Isobaric on a pressure volume graph is the horizontal line. Isochoric is the vertical line. And these two guys are the curves. So if you're dealing with those kind of processes, just knowing where heat and work go to might be worth taking a look at. We also had a student ask a question about elastic versus inelastic collisions. In an elastic collision, basically energy is not lost to non-conservative work. So in that case, you can use conservation of momentum, but you can also add up all the kinetic energies before. They'll be equal to all the kinetic energies after. So you have two equations in an elastic collision you can use. In inelastic collisions, you can only use conservation of momentum. And that's where you'd want to be thinking about using that. The difference between partially inelastic and totally inelastic is only really easy to see in the center of mass reference frame. If you go into the center of mass reference frame in totally inelastic collisions, all kinetic energy is lost. The two come to a stop. If you don't go into the center of mass reference frame, if they stick together, that's a totally inelastic collision. If they bounce off, partially inelastic. We spent a fair amount of time talking about the electrostatics unit. I feel like there's a lot of vocab here. But the key thing to understand is fields have to do with forces. If you are in, say, our classroom, this equation describes a gravitational force. It partially has to do with the object that you're moving or that is in that classroom, its mass. But a lot of it depends with where you are. 9.8 in the classroom would be the gravitational field. And you multiply the gravitational field by the mass to give you the object's force. So at the end of the day, force has something to do with the object times something to do with the location. You only can use this equation if you've got a single point mass that's causing the gravitational field, which is what we usually say for the Earth. That doesn't give students trouble, but when we get to electricity, it does. Got to be very careful. You can only use the electrical version of this if you've got a point mass. But you can always use the electrical version of this. If you know the electric field, what's going on with that location, multiplying the electric field by the charge gives you the force. Notice that in this location, the positive and the negative are experiencing very different electrical forces. But the field is in the same place there. So we can easily calculate their individual forces by multiplying by the charge. So the same is kind of true with potential and potential energy. They go together. If you are in a classroom, the potential energy of either of these objects is mgh. It's going to change based on how high you lift the object, but also what the object is. The GH part is the part that just depends on where you are. So that doesn't change for any object. You want the potential energy, you got to multiply its individual mass times the GH part. So potential is the where you are of potential energy. Same is true with electricity. If, let's say, you put charges between the plates of a capacitor, a positive charge really doesn't want to be here. Work would have had to been done to bring it here. And it's got a lot of potential energy. How much? mgh, except the electrical version is Q for charge, E for electric field, and D for distance. How far did you move it in the direction it doesn't want to go? How far did you move it against the force? Sometimes it's easier to visualize that in 3D. So here's that same picture. And we're kind of pretending here that we're dealing with gravity. We've almost moved a positive charge uphill, moved it away from where it didn't want to go. And we gave it the potential energy QED. We got to remember that negatives are always opposite. This positive charge would roll downhill just like a ball would. This negative charge would shoot uphill because it's opposite what the positive does. You can map out space around charges. You can give them electric field lines, and you can give them equipotential lines, which tell you essentially how much potential there is in that location, and you can figure out how much potential energy the object would have by multiplying charge times that potential. So you can make a map of potential for all sorts of situations where we have multiple charges, and we want to kind of think about what the equipotential lines might look like in 2 dimensions, how they'll be presented to us on paper or on a test. But then what would that represent if it was gravity? We would be gaining potential energy as we went towards up either of these peaks if we're talking about a positive charge or a mass. And as we go up, we'll have more potential energy. And as we roll down, we'll be losing that potential energy. Notice that for 2 similar charges, you have a saddle shape. You don't actually have a zero potential energy between them, because if you start going this way with a positive charge, it's going to repel back that way, and vice versa. So you're not ever at zero when you're here. We talked a little bit about circuits. I encourage students to really kind of review series and parallel. Not so much the specific math, but just the understanding how current divides up between branches. What's going to happen to the current if I take out one resistor or add an extra resistor. And I ask students to really use Kirchhoff's rules, again, for any complicated circuit, but also for their overall understanding. Kirchhoff's loop rule essentially is just conservation of energy. If I start here as a charge and I gain potential energy, I'm going to have to lose that potential energy to get back to the same place if I go around any loop. Just like a hiker leaving their car and going up a mountain, to get back to where they start, they have to lose all the energy they gained. So you can use the loop rules for any loop you want to relate energy gains and losses in the circuit. And since charge is conserved, any charge going into a junction has to come out, so the currents all have to add together. I wouldn't be super worried about a complicated calculation on the AP test, but I would definitely be thinking about what would happen to how energy divides up and how current divides up if, say, a resistor is removed or a resistor is put back in. And they might ask you questions about how things would change, and I'd be able to explain that in a sentence, how things would change. So the final question that was asked by students online before was about directions of forces on wires that are running parallel to each other. And I honestly recommend that if you haven't watched a magnet laboratory, watch this and just remember what you see there. As they say in the movie, it's hard to forget what it looks like when you run thousands of amps of current on wires right next to each other, both in parallel and then anti-parallel. You won't forget it. But if the question is ever what direction is the force and it's magnetism, the answer is always right-hand rule. So there's two right-hand rules really you should be paying attention to. And they are this right-hand rule, which relates force, motion of a charge, and magnetic field. This works both for particles moving through space and also for charges moving through a wire, as long as you assume there's conventional current. So positive charges are leaving the positive and going to the negative. I know that's not what really happens, but that's sort of how we talk about charges moving through circuits. You also should know this right-hand rule, where if you point your thumb in the direction of current, the magnetic field is in concentric circles in the direction your fingers are curling. So with those two right-hand rules, if we're trying to figure out the direction of force on the black wire due to the orange wire, we'll curl my hand and we'll see that where the black wire is, the magnetic field is pointing towards me. So now if we have a current going that way, parallel to the one on the orange wire, a field that way, my thumb tells us that we have a force on the black wire towards the orange wire. So parallel currents attract each other. Anti-parallel currents would push each other apart. So right-hand rule is really the only thing in the end you need to learn about that. I had one other thing I thought was worth mentioning about magnetism. I think it's worth knowing about an electron gun. If you have electrons forming near a negative plate or at a negative plate, and you put a positive plate across from that and put a small hole in it, an electron will kind of fall, just like a book would fall from a high height. It has a lot of potential energy when it's near a negative plate. It has a lot of kinetic energy when it gets farther away from that. And notice here we've just got our equation for potential energy of a charge. If we know the potential difference, we can figure out how fast it goes. Electron guns, this math is something worth knowing. Magnetic forces, they are just like any other force. So once you've got your free body diagram right, sigma F equals ma, even if it feels exotic, it's the same basic math and science you've been doing. So I hope this video was helpful. I hope the office hours were helpful too. I have one overall concern right now, which is please don't be spending your time worried about do you know every fact. You know a lot of facts. Right now it's about the big picture. Concept maps, mental alertness, getting a good night's sleep. When you get one of these questions, just do the best you can to figure out what kind of problem it is and start on it, and it'll be okay. So it was good to see everybody on the review today. I'm thinking about everybody though, and I want you to have confidence in this and do the best you can, and try to have a little fun with it. Take care.